On the top of the screen, we see the reaction of one butene with hydrogen and a platinum catalyst to give butane. A simple representation of this reaction coordinate diagram of this conversion is shown below. Let's place the dashed horizontal line from the energy level of the reactants and label the activation energy as the difference in energy from this dashed line to the top of the reaction coordinate. The platinum metal in this reaction is a catalyst that only affects the activation energy that is related to how fast the reaction occurs. For our discussion, how fast this reaction occurs is not important, since we are only interested in the potential energy of the reactants and the products. Let's remove the catalyst and the label of the activation energy. Now let's draw a second horizontal dashed line from the product and label the energy difference between the reactants and the product. When one butene is hydrogenated, 30.1 kilocalories per mole of energy is released in the form of heat. This energy that is released is called the heat of hydrogenation. Let's show this formally for this reaction by replacing energy released with a symbol for the heat of hydrogenation. In order to compare the heat of hydrogenation in different alkenes, we will replace the traditional reaction coordinate with a diagram depicting the reactants and products separated by a vertical line for the energy released. How does the heat of hydrogenation for one butene compare to other monosubstituted alkenes? In order to answer this question, let's replace the top reaction with two new 1-alkenes, propene and 1-hexene. Propene releases 29.9 kilocalories per mole of energy, and 1-hexene releases 30.2 kilocalories per mole. These data show an important point regarding heats of hydrogenation. For alkenes with the same substitution, in this case, monosubstituted alkenes, we can expect a release of energy that is very close, if not identical, to 30 kilocalories per mole. With this in mind, let's modify the bottom alkene and replace the alkene substituent group with an R group for the reactants and the products. Now let's look at disubstituted alkenes. First, we will look at two alkenes with trans-substituents, trans-2-butene and trans-2-pentene. When these are hydrogenated, they release slightly more than 27 kilocalories per mole of energy. Again, this is a general value for transalkenes, so let's plot this in the bottom section. As we would expect from the Part 1 animation, trans-disubstituted alkenes are lower in energy than monosubstituted alkenes. Let's now consider one more example by replacing the alkenes on the top with disubstituted cis compounds, cis-2-butene and cis-2-pentene, and show their heats of hydrogenation. We can see that the energy released in these two examples is slightly above 28 kilocalories per mole. In the animation on alkene stability Part 1, we discuss in detail how steric hindrance between alkyl groups forces cis-alkenes to be less stable than transalkenes. Let's now place the general value for cis-disubstituted alkenes on the lower part of the screen. From these heat of hydrogenation data, we can see that the energy level for cis-disubstituted alkenes is higher than trans-disubstituted alkenes. In summary, the release in energy from hydrogenation of an alkene is called the heat of hydrogenation. We can see that each group of substituted alkenes, monosubstituted, cis-disubstituted, and trans-disubstituted alkenes, differ in stability. This is a general trend that can be extended to trisubstituted and tetrasubstituted examples. In our discussion, we indicated that the more substitution on the carbon-carbon double bond gives more stable alkenes. This is also a general trend. Finally, heats of hydrogenation tells us that trans-disubstituted alkenes are more stable than cis-disubstituted alkenes. This is also a general trend. The reasons for these trans instability are discussed in the animation Alkene Stability Part 1. If you liked this video and would like to see more, please give it a thumbs up and subscribe.